Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules.
Welcome to Lesson 17, Characterize points on a perpendicular bisector. Classwork opening exercise says, in Lesson 3, you bisected angles including straight angles. In other words, a 180-degree angle is a straight line. You related the bisection of straight angles into Lesson 3 to the construction of perpendicular bisectors in Lesson 4. Review the process of constructing a perpendicular bisector with the segment below. Then complete the definition of perpendicular lines below your construction. Okay, so we're going to use the compass and straight edge. Let me get those. There's the compass and there's the straight edge. All right, so first thing I'm going to do is switch colors. And I'm going to put the compass, if you remember from Lesson 4, you put it at the end of the one end of the line, and you construct a circle. And then you move the point to the other end, and you construct a second circle. And when you do that, you then have two circles that intersect, and if I put the 0 as close as I can to the one place where the two circles intersect and rotate it like so and draw a line, there is a perpendicular bisector. Okay, so now that I put the ruler here, you can see that starting at 0, the length of this segment is 7 centimeters. So halfway point of 7 centimeters is 3.5 centimeters, which is right here. So I'm just a little to the left, but look how far off the diagram is that they gave in the book. It's off by 2 more millimeters. And this line is not horizontal with the screen, as you can see with my ruler. So anyhow, that's how you make a perpendicular bisector from Lesson 4. Okay, now we do finish the definition, and it says 2 lines are perpendicular if they blank, and if any of the angles formed by the intersection of the lines is a blank angle. 2 segments are perpendicular if the lines containing them are something. Okay, so it is 2 lines are perpendicular if they intersect, and if any of the angles formed by that intersection of the line is a what kind of angle? A right angle or 90-degree angle. 2 segments are perpendicular if the lines containing them are perpendicular. Discussion. The line you constructed in the opening exercise is called the perpendicular bisector of the segment. As you learned in Lesson 14, the perpendicular bisector is also known as the line of reflection of the segment. With a line of reflection, any point on one side of the line, pre-image, is the same distance from the line as its image on the opposite side of the line. So example 1 says, is it possible to find or construct a line of reflection that is not a perpendicular bisector of any of the segment connecting a point on the pre-image to its image? Try to locate a line of reflection between the 2 figures to the right without constructing any perpendicular bisectors. Okay, so here's what we would do. And just pick blue for a change. So obviously if I drew this like so, this point here is much closer than this point over here. So what you have to do is adjust so that it looks like it's the same distance apart. Now this is too close, it's closer than this point. So move that closer, and eventually you will find a point where this line segment will be equidistant from this point and this point. This point will be the same distance from here as it would here, and this point the same distance from here as this point would be to here. So it would probably be somewhere around there. So it says try to locate a line of reflection between the 2 figures to the right without constructing Any perpendicular bisectors. Okay, so that's probably about the right place, because just to check this now, there's two segments, so that doesn't look right now that I've done that. So is it possible? It's really, actually, it's quite hard. It's quite difficult. So it'd be probably more along the lines of here. So with perpendicular bisectors, it does make it much easier. Okay, page 2 brings us to a discussion. Why were your attempts impossible? Look back at the definition of reflection from lesson 14. For a line L in the plane, a reflection across L is a transformation R sub L of the plane defined as follows. For any point on the line L, R sub L of P equals P, and for any point P not on L, R sub L of P is the point Q, so that L is the perpendicular bisector of the segment PQ. So you really need to be accurate. So the key lies in the use of term perpendicular bisector. For a point P not on L, explain how to construct the point Q so that L is the perpendicular bisector of the segment PQ. Okay, so let's think about that problem from another perspective. We have determined that any point on the pre-image figure is the same distance from the line of reflection as its image. Therefore, the 2 points are equidistant from the point at which the line of reflection, perpendicular bisector, intersects the segment connecting the pre-image point to its image. What about other points on the perpendicular bisector? Are they also equidistant from the pre-image and image points? Let's investigate. So here's example 2. Using the same figure from the previous investigation, but with the line of reflection, is it possible to conclude that any point on the perpendicular bisector is equidistant from any pair of pre-image and image points, G to its image H? How can you be certain that GP equals HP? Okay, well, I suppose we could measure it, so let me get a ruler, bring it down, and put the ruler right on G, rotate it to P, like so. That is 4 centimeters. So now if I move my ruler here, rotate it up to H, like so, trying to be as accurate as possible. And it looks like that is also 4 centimeters. If R is the reflection, then R of G, the reflection of G, equals H, and the reflection of P equals itself because it's on the line of reflection. Since R preserves distances, GP is equal to HP. Okay, page 3, discussion. We have explored perpendicular bisectors as they relate to reflections and have determined that they are essential to reflections. Are perpendicular lines, specifically perpendicular bisectors, essential to the other 2 types of rigid motions, rotations and translations? Translations involve constructing parallel lines, which can certainly be done by constructing perpendiculars, but are not essential to constructing parallels. However, perpendicular bisectors play an important role in rotations. In lesson 13, we found that the intersection of the perpendicular bisectors of 2 segments connecting pairs of pre-image to image points determine the center of rotation. So example 3 says to find the center of rotation for the transformation below. How are perpendicular bisectors a major part of finding the center of rotation, and why are they essential? Okay, so I'm going to draw a segment. Now I should do this with the ruler, and I will. So here's what we do. We get a ruler, and let's do it in purple. So we're going to take the vertex of this triangle, this point right here, and we put our ruler 0 right on it, rotate it to the other, and draw a segment from pre-image to image. Now I made that a little bit too long. Okay. Thought I could make that a little bit longer, like so. Still a little too short. I erased too much. Okay, so right there. So there's a segment connecting the pre-image to the image. So then we do it again. This time I'll use green. And this time I will choose the angle that's closest to 90 degrees. Doesn't matter which two you choose. Just make sure you go to its pre-image and not the wrong vertex. So then draw a segment from there to there. All right. So there are our two perpendicular bisectors. I misspoke. There are our two segments that connect two pre-images to two images. Okay, so now that we've drawn these segments, we're going to take a compass. We put the compass at one end of the purple line, rotate it, open it, so that it's right on the other end. Got to move it a little bit on this end. Draw a circle. Move it to the other end. Draw a circle. And construct the segment that goes through the circle's intersections. Okay, now we're going to do the same with the green. So I'll move my compass to the end here, like so. Rotate it so I'm on the line. Open it so I'm at the end. Draw a circle. Move the compass to the other end, so we're drawing a circle centered at the other end of the segment with the radius of the length of the segment. Draw another circle over here, and then get our ruler, put 0 right on one of those circle intersections, rotate it up like so, and draw a segment. Okay, so this is off just a little bit. They have a dot there, but I calculated the two perpendicular bisectors to intersect right here. So let's get rid of these circles because it's hard to see. Okay. So I got this point here is the center of rotation, not this. Okay, again, I could have been off a little bit because of the technology. So why are they essential? The center of rotation is the intersection of two perpendicular bisectors, each to a segment that joins a pair of corresponding points between the figure and its image. Okay. As you explore this figure, also note another feature of rotation. As with all rigid motions, rotations preserve distance. A transformation is said to be the distance preserving or length preserving if the distance between the images of the 2 points is always equal to the distance between the original 2 points. Which of the statements below is true of the distances in the figure? Justify your response. So what they're saying is segment AB. They're saying segment AB is equal to segment A prime B prime. Okay, and they're saying segment A prime is equal to B prime. Okay, which of the statements is true? If I measure these, that is 52 millimeters. That was B to B prime. And this one is 60 millimeters. So these are obviously not the same length, as you can see as I put them closer to each other. One's longer than the other. So the true statement is AB is equal to A prime B prime. Okay, page 4 brings us to an exercise. So now it's your turn. Pause the video, see if you can do this, and then come back. But if you want to wait for me to read the directions, then pause, please do. In each pre-image combination below, A, identify the type of transformation. B, state whether perpendicular bisectors play a role in constructing the transformation, and if so, what role? And C, cite an illustration of the distance preserving characteristic of the transformation. For example, identify two congruent segments from the pre-image to the image. For the last requirement, you have to label vertices on the pre-image and image. So pause the video, do these 4 problems, and then unpause the video and check. Okay, so here we go. So looking at this, if I had a point, I don't know, maybe somewhere around there, and I rotated it 180 degrees or maybe negative 180 degrees, this is the image we would get. So this is a rotation. And is the perpendicular, did you use a perpendicular bisector to do this? And the answer is yes. And for what? And it was to construct the center of rotation. So we say to construct the center of rotation. Examples of distance preservation. Okay, so if I label this A and this B, rotate that around, this would become A prime, this would become B prime, and I'd say A, B equals A prime, B prime. It says to identify two. So then if I named the next point C, then this is C prime, and I could say BC is congruent to B prime C prime. Or the length of BC is equal to the length of B prime C prime. Okay, number 2, this is not a rotation. This got moved to here. So let me do this. Let me do a ray, and in this case it'd be called a vector. Let me draw a vector from here to there. Vectors tell us direction and distance. So that distance there and that direction should be the same for every single point, like there, and right here, and right here. So that is definitely a translation. Perpendicular bisector? Nope. Examples of distance preservation. Again, just name a segment on the original, name the segment on the image with prime, and say AB equals A prime B prime. Translations preserve our distance, lengths. So if I then continued, let me get this vector out of the way, move it Victor, okay. This would be C, and this would be C prime. So then I could say BC equals B prime, C prime. Okay, these are just examples. There are multiple solutions to this. If you're going to choose two, there's 1, 2, 3, 4 to choose from. So you might have two different ones than me, or one of these and one different one. Okay, this number 3 appears to be a rotation. So the point of rotation is right here, because if this was A, B, C, D, E, then this would be A prime, B prime, C prime, D prime, and this is E comma E prime at the same location. So when that occurs, that is your point of rotation. So this is a rotation. Okay, I can't spell. Rotation. Perpendicular bisector. Okay, so this one's a little different. In general, yes, we could use a bisector, but not necessary here. Okay, it's not necessary in this one because we know the point of rotation is right here. So all we would use is a protractor. Examples of distance preservation, choose anything. AE equals A prime E prime. BC equals B prime C prime. So that would be here is equal to here. And I suppose I should use a straight line to show these. And AE is here is equal to A prime E prime. Okay. This one, it's definitely not a translation. If I rotated this, this point would be here, and it would look like so. Something like that if I rotated it. So it's not a rotation. It's not a translation because this is flipped over, and that there then would have to be a reflection. So if I drew a line of reflection and tried to make it the same distance from every point on the right to every point on the left, then it would be somewhere about that. So the transformation is a reflection. Perpendicular bisector, yes. To construct the line of reflection. Examples of distance preservation. Ready? If I name this A, B, C, D, then this would be A prime, B prime, C prime, D prime. Choose any one of these sides. Doesn't matter. I could say A, let's try a segment. I could say A, D is the same length as A prime, D prime. Okay, and then another one, doesn't matter which ones we choose. Let's just go with B to C is going to be the same length as B prime to C prime. Okay, so there you have it. Okay. Page 5 brings us to question 5, and it says, in the figure to the right, GH, segment GH is a segment of reflection. State and justify two conditions about distances in this figure. At least one of your statements should refer to perpendicular bisectors. So here could be one statement. It says each point and its reflected image are the same distance from the line of reflection. So let's take a look. So if I pick a point, it doesn't matter which one, how about A, and line up my 0 with it, we're going to measure as accurately as possible. There we go. From A to the segment GH is 21 millimeters. Then if I move my ruler so that 0 is right on G, like so, and rotate it, this distance is also 21 millimeters. So A to here and from here to A prime are equal, and that's what this says. And that is true for every point in this diagram. E is equal distance from E prime, F and F prime. H, J, and I are on the line, so their distance from GH is 0. So their image distance would be 0 from the line. So one of our statements has to mention perpendicular bisectors. So here we go. The line of reflection is the perpendicular bisector. The line of reflection is the perpendicular bisector of the line connecting each point with its reflected image. So this point right here is the perpendicular bisector of A to here. So for instance, no matter what point I choose here, if I drew a perpendicular bisector, then the line of reflection is going to be perpendicular to the lines that connect each image. So let's pick a different one just for instance. So if I chose D and drew a segment from D to D, yeah, it's snapping on my 90 degree or horizontal. So that's the best I can do. I can't get that to not snap. Oh, snap. Alright, how about right there? Nope. Oh, come on, man. Of course, they created it. There we go. That's the best I can do right there. So that's a perpendicular bisector. This distance is equal to this distance, and this is 90 degrees. Okay, page 6 brings us to the end of lesson 17. Go to your problem set.